So those two events we just looked at were examples of independent events. Now, terminology-wise, our two events are independent. So A and B are independent if and only if. That means this is a definition. So if they're independent, then these two statements below are true. And if these two statements below are true, then A and B are independent. That's where the if and only if comes in. So over here on the left-hand side, we're saying that the probability of A happening given B happens is just the probability that A happens. So B happening did not change the probability of A happening. Okay. And then just reversing roles, over here on the right-hand side, this is saying the probability that B happens given or knowing A happens is just the probability that B happens. So whether or not A happens does not affect the probability of B happening. That is the definition of independence. Now, if those probabilities are not equal, then we have dependent events. Let's take another look at our two-way table. And again, I'm going to randomly select one person, and we want to investigate this idea of independent events or dependent events. So first I want to find the probability that the person owns an iPhone. So there are 4,536 to choose from. 1,764 of those own an iPhone. Okay, we've done that one enough times by now. It should be pretty easy. Now I want the probability they own an iPhone given they're in the 26 to 40 age group. We're limiting ourselves to 26 to 40. There are 1,296 to choose from, and 504 of those are iPhone owners. Okay. So my two events here are owning an iPhone and being in the 26 to 40 age group. Those are the two events we're investigating. Okay. So now I'm going to take the perspective from the age groups. So I want the probability that someone randomly selected ends up in this age group. Well, there are 4,536 to choose from, 1,296 in the 26 to 40 age group. So that is our probability, the fraction, 1,296 over 4,536. And the conditional probability, the probability that they're in this age group given they own an iPhone. Okay. So now again, we're interested in knowing they own an iPhone, what are the chances that they end up in this age group? As opposed to part B, which said, knowing they're in this age group, what are the chances they own an iPhone? Okay, so here, we're only interested in iPhone owners. Okay, so there are 1,764 of those to choose from, and 504 of those actually do fall in the 26 to 40 age group. So that's our probability. Okay, so here we have two of our conditional probabilities along with the individual probabilities of owning the iPhone and being in the 26 to 40 age group. So the question I have is, based on these results, we can determine whether or not owning an iPhone and being in the 26 to 40 age group are independent events. So to do that, we need to look at the probabilities that we just calculated and relook at the rules for being independent events. So remember, two events A and B are independent if and only if the conditional probabilities, the probability of A given B, is equal to the probability of A, and similarly, the probability of B given A is equal to the probability of B. Okay? So these are the four probabilities we just calculated a second ago. So let's take a look at it. Okay, so here, owning an iPhone is my event A, being 26 to 40 is my event B. So the probability that I own an iPhone, given I'm in the 26 to 40 range, would be 504 out of 1,296. Okay, now, the probability that the person selected was an iPhone owner, we found to be 1,764 out of 4,536. Now, the question is, are those two probabilities equal? Okay, take a second to check it out. They don't look equal, but if you grab your calculator, they are in fact equal. Okay. So the fact that the person was in the 26 to 40 age group did not change the probability that they owned an iPhone. The probability of owning an iPhone within that age group was just the probability they owned an iPhone. Okay? So those were the first two probabilities, part A and B, we did a minute ago. Now if we look at C and D, we had the probability that they were in the 26 to 40 age group given they owned an iPhone, which we found to be 504 out of 1764. Okay? And the probability that they were in the 26 to 40 age group, 1296 out of 4536. So again, I ask you, are these equal? Okay? So if you grab your calculator, check it out, and you'll find they are in fact equal. So owning an iPhone did not change the probability that they ended up in this age group. The probability they ended up in the 26 to 40 age group, given they owned an iPhone, was just the probability that they were 26 to 40. So if we put these two together, owning an iPhone did not change the probability of being in the 26 to 40 age group. And whether or not they were in the 26 to 40 age group did not change the probability they own an iPhone. Okay, so we have satisfied the definition. Right? So owning an iPhone and being in the 26 to 40 age group are in fact independent events. So let's look at what are now called AND problems. So problems where more than one thing has to happen at the same time. So I want the probability that when we randomly select one person, this person owns an iPhone and simultaneously are in the 41 to 55 age group. So remember, whenever you can count, count. All right? So in this case, I want to know how many are there to choose from? Well, we're choosing one from everybody, and all 4,536 are equally likely to be the one person that we choose. Now, out of those, we need someone who owns an iPhone, so it'd have to be someone here in the first row. Okay? And they need to be in the 41 to 55 age group, so they'd have to be in this third column. So we have exactly 642 people that both own an iPhone and are in the 41 to 55 range. So the probability we're looking for, well, our denominator, how many are there to choose from? 4,536. Out of those, how many do what we want? And the answer is 642. So the probability is simply 642 out of 4,536. Because in this case, I could easily count. So often when we have these two-way tables, right, the probability of being in a particular row and a particular column is an easy counting problem. So for example B, we want the probability that they're an Android phone owner and in the 26 to 40 age group. So I'm going to let you do this one. So there are 4,536 to choose from. We want the ones that both own an Android are in the 26 to 40 age group. That's 638. So hopefully you got 638 out of 4,536. Now one last time. We want the probability that they're both in the 10 to 25 age group and over 55. So we're going to pause and practice. I want you to do this problem. Pause the video. Let's check and see if you got things right here. So there are 4,536 to choose from. Okay. We want someone who's over here in the 10 to 25 age group on the left, and at the same time in the over 55 age group. Well, how many people are between 10 and 25 years old and also over 55? Of course, the answer is 0. The probability that they fall in these two categories at the same time is 0. So we would have 0 over 4,536 if we wanted to write this as a fraction. Or we can just write the number 0. Those are equal. Okay? And remember that a probability of 0 means it cannot happen. It is impossible for someone to be 10 to 25 and at the same time over 55. Those two events are disjoint. With our AND problems, we always want to try and start counting first. Now, if that's not possible, we're going to use a multiplication rule. We want the probability of two events, A and B, both happening at the same time. Well, only a certain percentage of the time will event A happen, and out of that, B doesn't always happen. So what we need is a percentage of a percentage, and that's exactly what's happening here when we multiply our probabilities or proportions together. So we got the probability of A multiplied by the probability that B happens given that A happened. All right, there's a percentage of time that A happened, and only a percentage of that percentage does B also happen. That's what this formula is doing. Now, if we expand to allow a third event in, then the logic's still going to be the same. Right? Only a certain percentage of time does A happen, and when that happens, only a certain percentage of time does B also happen. And when A and B have both happened, only sometimes does C also happen. So we need the probability of the first thing, A, multiplied by the probability of the next thing, B, given that A happened. And then we'll move on to the next event, C, and we need the probability of that happening given all the previous events, in this case A and B have happened. Okay. So if we wanted to expand this to 4 or 5 or 9 or 20 or 100 different events that all must happen at the same time, the logic is still going to be the same. We start with the probability of the first event, probability of A. Then we do the conditional probability, the probability of the next event happening given the previous event has happened. And then we move on to the next probability, the probability of the next event happening given all the previous things have happened. And we keep going with these conditional probabilities until we run out of events we're interested in. This formula does simplify in some cases, right? So if A and B are independent, remember that means that the probability of B happening given A happens is just the probability that B happens. Okay? So that second term simplifies. So when you have two independent events, A and B, you can just find the probability of the first thing happening, find the probability of the second thing happening, and when you multiply those two probabilities together, that is the probability of A and B happening. But this only works when your events are independent. And if your events are dependent, then that second probability must be the conditional probability. One last thing I want to remind you of, right? That is, the probability of A and B happening at the same time is equal to 0 if and only if these events are disjoint. Remember, disjoint events are events that can't happen at the same time. So we saw this earlier when we had the probability that a random person was in two different age groups. Okay, they couldn't be in both age groups, so that probability of being in the first age group and the second age group was 0. So now let's look at an example where we actually need to use the multiplication rule. So we're going to roll 5 fair 6-sided dice. Now, if we tried to keep track of all the possible outcomes with these 5 dice, that would be 6 to the 5th power. That's a humongous number. So we can't just count up all the options and see how many of them give us what we want here. We're going to have to take and use the AND rule, the multiplication rule. So the first thing I want to know is, what's the probability that all 5 dice are even? Well, I want you to notice here that for them all to be even, 5 independent or 5 separate events have to happen at the same time. That is, the first one has to be even, and the second has to be even, and the third and the fourth and the fifth have to be even. So even though this probability does not say that it's an and problem, the fact that it requires 5 things to happen simultaneously makes it an and problem. Okay? So we're going to handle this with our multiplication rule, and we're going to start with the first outcome. So there's 5 things that have to happen, but I'm only going to worry about the first one first. So the probability that the first die is even is 1/2. Okay? So this is my probability of A from the rule. Now I need to multiply this by the probability of the next thing happening, given the fact that we already got an even to start with, because we're only interested in the case where we end up with all evens. Well, whether or not the first die was an even number doesn't change the probability of the second die being an even number. Right? So each outcome of each die are independent. So the probability the second one is going to be even, given the first one was even, is still a half. Now, knowing the first two are even doesn't change the probability of the third one being even. The probability the third one's going to be even, given the first two were, is still a half. And the probability the fourth one is even, given the first three were even, still a half. And finally, the probability the fifth one is going to be even, given all the others were, still a half. All right. So here, this will simplify down to 1/2 to the fifth power, which is the same as 1 over 32 or 0.03125. Now, notice here that our 5 events were independent, so we just got to take the probability of each one being even and multiply those 5 together. That's the advantage of the independence in an AND problem. So let's look at one more example with the 5 die. I want the probability that we roll a 1 with the first die, a 2 with the second die, and so on. So we end up with the 1, 2, 3, 4, 5 rolled in that order. Well, again, we're going to worry about the first thing first. We want the probability the first one is a 1. Well, that probability is 1/6. Now, knowing that we got the 1 to start with, what are the chances that the second die is going to be a 2? Well, the first one being a 1 does not change the probability of the second one being a 2. So the probability the second one is a 2 is still going to be 1/6. And the probability the third one is a 3 is still going to be 1/6. And the probability the fourth one is going to be a 4 is 1/6. And the same thing for the fifth one. So this also, again, because whether or not the first roll is even or whether or not the first roll is a 1, those do not change the probability of future rolls. Right? Because the outcome of each roll of the die, the 5 dice, their results are independent. Okay? So when you have independent events, and rules are really just find your individual probabilities, probability of A, probability of B, probability of C, D, E, and then multiply all those together. So now we're going to use this two-way table, the example that we've been using throughout the course of this video, to investigate an AND problem. We're going to randomly select 3 people, and we care about the result of each of the people. We want none of them to end up owning a smartphone. So this is an AND problem because we have to have the first one doesn't own a smartphone, and the second one, and the third one does not own a smartphone. So we're going to tackle this problem 2 different ways. One, we're going to tackle it assuming the people are selected and then replaced. So that means every time we make a selection, we're going to put them back before we make the next selection. Okay? So when we go to choose our first person, even though I want 3 people, none of them owning a smartphone, that's an AND problem. I worry about the first thing first. So what's the probability the first person does not own a smartphone? Well, at this moment, there are 4,536 to choose from, and out of those people, 756 do not own a smartphone. So that's my probability that the first person, person number 1, is not going to own a smartphone. Now we need to multiply this by the probability the second person does not own a smartphone, given the first one didn't. So at this moment, we have just selected a person, person number 1, and put them back in the pool. So this is where that mantra that we've been going throughout the course of this chapter, when you go to figure out your calculations and your probabilities and your fractions, at this moment, how many are there to choose from and how many of those will give me what I want? So we selected number 1, put them back. So when I go to number 2, how many are in the pool to choose from? Still 4,536 in there to choose from. And out of those, there are 756 that do not own a smartphone. So now we're going to move to the third person. So we want the chances of the third person not owning a smartphone given the first 2 people didn't. Well, remember, those first 2 people have been put back in the pool. So at this moment when I go to select person number 3, how many are there to choose from? Well, 4,536. How many of those do not own a smartphone? Once again, 756. So because we did our selections with replacement, each selection had an independent outcome. What happened on the first and the second and the third did not affect the probabilities of all the other selections. So we end up with a grand total here after we multiply it out of 0.0046296296, and it probably goes on like that for a long, long time, I'm guessing. Okay, now we're going to tackle this problem assuming the people are selected without replacement. So again, worry about the first one first. When I go to choose the first person, there are 4,536 to choose from, and 756 of those do not own a smartphone. The first probability is the same regardless of whether we're doing with or without replacement. But on the second one is where we get our change. So when I go to choose the second person, remember we've taken one person out and we are keeping them out. So at this moment, when I go to select person number 2, how many people are there to choose from? Well, we've lost one. So there's 4,535 to choose from. And how many of those do not own a smartphone? Well, we've already thrown out one person who did not own a smartphone. So there are now only 755 who do not own smartphones. So as we move to the third person, there are now 4,534 to choose from because we've already thrown 2 out and not put them back. And since we're only interested in the chances of the third one not owning a smartphone, given the first 2 did not own a smartphone, then there are 754 people in the pool who do not own smartphones. And so you notice how the second and the third fraction changed here without replacement because the events are dependent. What happened on the first one and the second one, they do change the probabilities on the third and the fourth and so on, right? When we do this without replacement, because once you take something out and you keep it out, the pool has changed. Now I'll grant you, in the end here, because we only did 3 people out of 4,536, right? The probabilities here are very similar. But we do have to pay attention as to whether or not our events are independent or dependent. Okay. Now, in practice, there is no reason to assume that things are going to be done with replacement. You should always assume that they're without replacement. Right? You don't really want to select the same thing twice in most cases. So you have to think about the context of the problem to decide whether or not you're going to do it with or without replacement. If you're allowed to reselect something, then you're doing it with replacement. If you're not allowed to reselect something, then you're doing it without replacement. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!